Okay, I want to go over my do file for this scores activity, which we've been working on for a few weeks here. And I'm going to walk through. I've already got the do file written here, and I'll share that with everyone. And I want to walk through this and just explain everything that's happening because I've learned a couple things about useful commands. So first thing, I'm just going to run this line by line. I'm going to run line 2, import data set. So I put it on my desktop. I import it. We get what you guys have expected. We've got different variables. The first issue that we're going to deal with is this household income variable. It is 56K, but we really just want it to be a number. And so we want to take that K off and then tell it to treat it like a number and not like a string. So that's the first thing I'm going to do is line 5 is going to take the K off. And basically this is a regular expression. You can look into more of those, but this is the key piece and it says, hey, just take the numbers 0 to 9, which are all of the numbers. Just extract the numbers. So if I run that, I get this income variable pop up over here, which is good. But you're going to notice something. It's still red, which means Stata is still thinking of it as a string. And I want Stata to think about it as a number so I can add, multiply, take the mean, all of that. So what I'm going to do instead is and I didn't realize this, but it's great. So dstring income, and before we had done like a generate here, which made a new variable, but I found out that there's an option for replace, which will basically just write over the old variable and make it a number. So now we can see here, state has made it black, which is fantastic, means it's thinking about a number. I no longer need this household income variable, so I'm going to run line 7 to drop that. Now, next order of business. So that's great. Income looks fantastic. Next order of business is dealing with this test score column where we see what the name of the test is, and then we have a number on the end, name of test, and then number. And the first thing what we want to do is we're going to generate the score. So we're just going to take the number out of it. Again, I need to do this dstring, and now I have the score, which is perfect. Generate score, grab the number, did a dstring. To generate the test type, I'm going to get the letters in here, A to Z, and that looks great. It just got reading. You might wonder why didn't it pick up the SS? Because it goes from left to right, and it picks up all the letters, and then it stopped when it saw that underscore, and it said, okay, well, what was that? Now I should add in, I can add something in here, which is we no longer need this test score. So I can drop that. I'm going to drop test score. This is this column because we've extracted the information into other places. All right, great. Now what I want to do is each student in this data set has two rows. 294 has a row for the reading score. And then if I look down here somewhere, I'll find a 294 and I'll find their math score. And I don't want that. I wish the data was wide in that I had one row for the student and then a column for their reading score and a column for their math score. And so what I'll do to get that is I'll run this reshape line and I wanted to make it wide. This was the row thing that I wanted to do. This was the way I wanted to spread it. Score was the important variable, and then string option was to say like, hey, those variable names are already strings. We had talked about that, and I think people had gotten that pretty well. Now my data looks great. I've got student ID. It's sorted it for me. I've got the student score on their math, the student score on their reading, the class size, the gender, and then their income. And I can look at descriptives. If I just tab class size, I can see, okay, there's 240 students in large class sizes, 160 in medium, 80 in small. I can likewise look at gender. Looks like we have a few more males than females. I can look at a cross tabulation between gender and class size, which is really good here. And that tells me a little bit more. It looks like, I don't know, you don't see any gigantic differences. I guess males, there's more in medium class sizes, but there's fewer in small class sizes. Maybe that tells you something. Um, but really what I want to look at is visually. And so if I run this histogram income by class size, well, this makes a really cool plot. And it shows me a histogram of the income for each class size. And the first thing you should notice here right away is just comparing the small and the large. is small class sizes, students have larger household incomes. So richer students are winding up in smaller class sizes, and the poorer students are winding up in large class sizes, and it looks like medium is somewhere in between. And well, that's interesting for a few reasons. First of all, why might that be the case? I guess rich parents might be bribing school leaders. They might be more white, and there might be some sort of advantage to being white in this school with how decisions are made. There could be a lot of different reasons. They could have come from a um, different school in the past and been funneled into a small class size in some particular way. And it's also a validity threat. We're interested in figuring out to what degree is a small class size more effective than say a large class size. And now we know that students in the small class size come from richer households. So if I see a student do better in a small class size than a larger class size, I have at least two explanations. One, it could be that the small class size is effective and students are learning more and therefore their score is being driven up. Second of all, it could also be that the student is just richer and has other advantages and it's not related to the class size. And that'd be dangerous. I might come up with the wrong explanation. I can also make one of these for scores. And so similarly, I can see that students in small class sizes do better on their math test than students in large class sizes. Again, I have two explanations. One's the income effect, two is the class size effect. You could come up with other stories as well. We'll skip the reading one, but that's an option too. So now I'm going to go down to to Anova. And what Anova basically just lets you do is, let's get rid of this graph guy. What ANOVA lets you do is there's these three groups, class sizes. There's small, medium, and large. And it says, hey, are the means of these three groups different than one another? That histogram very much said that the answer is yes. We saw that the means were clearly, clearly, clearly different. Um, and this does it in a statistically sophisticated way so we can actually tell if there was some sort of randomness. What it does, it gives you this F statistic and then it gives you a p-value. The p-value is the probability we would see such an extreme result if there wasn't an actual difference. Well, that probability is extraordinarily low. It's 0.00000, and we don't know after that, but assumes a bunch more zeros and then a one somewhere. And so what that tells us is we can reject the hypothesis that all of the means are the same, and we can say, okay, the means in income across class size are different for sure. And that's obvious, but you do need to do it in a statistical way. We do the same thing with score on math. Again, the p-value is really small, telling you that students perform differently in different class sizes. We can do it on score reading, and now our p-value is 0.06, which is interesting. It's right on the threshold. Right on the threshold. Usually we use a threshold of 0.05 as our alpha. So in this case, we would actually not be able to reject that all the nulls are the same. And we would have to say that we don't have evidence that the reading scores are different by class size. I guess might be interesting with that in mind to look at the histogram. And I guess that kind of bears out. It looks like there might be some differences, but it would be hard to say that those differences aren't for sure a result of just some sort of randomness in the data. Now, the tool to really dive in and to understand this sort of effect best is regression. And what I want to do is I want to predict the math score. So if I'm going to run this regress command, I always put the variable, my dependent variable, the one I'm going to predict first, and then what I'm going to predict, it, how I'm going to predict it after that. And so we might want to use class size to predict the math score. I'm going to run that. And I get this no observations error, which is a terrible error because it doesn't tell you what's going wrong. But what what's happening here is class size is a string, and regression doesn't play well with strings. It needs to do something funky to that string in order for it to work. And so this is where we're going to use encode. And I think people are wondering the difference between dstring and encode. What dstring does is it literally takes, if there's a number in red, it turns it into if it's a string but it's a number, it turns it into an actual number. That's what dstring does. Encode takes a string and it's going to assign a number underneath each of them. Excuse me. And so maybe small is going to become 0, mediums become 1, and large is going to become 2, for example. And so this is going to create what's called a factor, which is basically a number underneath, but it has a text label on top of it. And so when I run this, I now have class size factor over here, and you see that's delineated um, by blue. And a trick here is if you want to know what the number underneath is, when you click, it shows up here. So large is 1, medium is 2, and small is 3 because it's showing up here. Now I can run my regression. And so this gives you some of that Anova stuff as before. But really what we want to do is we want to look down here at the coefficients. So this says the intercept is 89.3. And then the class size factor is 10.2. And so in order to think about what that means, we need to go back and remember what these things are. So large class size factor was 1. And so what would you predict for a large class size? Well, you'd predict the constant 89.29 plus 1 times 10.2. So large is 89.3 plus 1 times 10.2. Similarly, medium is the same. It's 89.3 plus 2 times 10.2. And then small, that value takes a value of 3. So it's 89.3 plus 3 times 10.2. And so you can see this, what's happening is every time we go to another smaller class size level from large to medium or medium to small, we're going to increase our predicted test score by a factor of 10.2. Now, there's a problem with that, and why I don't want this here, is it's not treating this as an actual factor. It's treating those as continuous variables 1, 2, and 3. And so baked into this model is this assumption that every time I go, that going from large to a medium is a 10.2 difference, and also that going from a medium to a small is a 10.2 difference. And you can see that's kind of problematic, right? Like that's not necessarily the world in which we live. It could be a case that large to medium doesn't matter, and then medium to small is a huge effect, or something alternative could be the case. And so in order to have it actually treat it like a factor, I'm going to sneak in this little I dot first, and now we're going to see what happens. Now I actually get different values for the medium and the small. And so how I run this is large, I'm just going to predict the 99.26. Medium, you're going to predict 99.26 plus 11.15. And then small, you're going to predict 99.26 plus 19.94. And so that's interesting. Going from a large class size to a medium has an effect of positive 11.15. And then going from the medium to small has an effect of what's 19.9 minus 11.1, something like 8.8, something like that. And so there's a little bit of a difference there. And that feels better because we're using a factor. Now, to go back to the fundamental point of this, which was, hey, what's the effect of class size? It looks like the naive scientist might be willing to say, oh, going from a large to a small class size boosts test scores by 19.94 points. Now, remember that income graph. Remember that students in small class sizes come from richer families. We haven't done anything here to correct for income. We've done nothing to correct for the fact that the families could be richer. So this 19.94 is combine the income effect and the small class size effect, and there's no way for us to disentangle that here. And so this is the miracle of regression and why it's a super common tool in a lot of research is I can control for income. I can take income out of the equation, so to speak, by adding it into the regression. And so now when I run this regression where income's also in there, I'm going to be able to see both the effect of income and the effect of class size. And so let's see what happens there. I now have an additional variable of income, and my effect from small class size dropped to 14.55. And that's because the positive income effect soaked up some of that. Before it was 19.94. Now it's 14.55 because this 0.12 of the income has soaked up some of that difference in means. And so that's really, 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 really interesting. And so we can see here, and you can look over here at these confidence intervals and these p-values. Basically, this p-value is just as with the chi-square, or just as with the Anova, it's close to zero, which means this is certainly significant. This is certainly significant. We can have a confidence interval on this, which we didn't talk too much about this, but it says, hey, we're pretty sure it's in between 7 and 21. No, we're not positive that's exactly 14, this effective small class size, but we're pretty sure it's between 7 and 21. Interestingly, the income, despite it being positive, it's not quite statistically significant. It has an effect on the small and medium class sizes, but it's still a p-value of 0.096, um, which is interesting. And so I want to show you how to predict. So like, what if we want to predict a student in a medium class size with income of 100K? Well, what would we do? We're always going to start with that constant, 95.75. And then I'm going to add on the effect for being in a medium class. And then I need to add on, I don't add on 0.12, I add on 100 times 0.12 because this is multiplied by the income. This says for every $1,000 additionally in your family, you're going to have about an additional 0.12 increase in your test score. And so this is the equation I would solve right here. 95.775 plus 8.57 plus 100 times 0.12. I don't have a calculator out in handy to calculate that, but you can easily calculate that and imagine it's going to end up, I guess what this is about 12, that makes this about 20. It's going to end up about 116 or so. Would be our prediction for that student. Now we're not sure that that's going to be the exact student's test score, but it's our best prediction based on their class size and their income level. So case here, what's the storyline? Yes, class size has an effect. It looks like income probably also has an effect. To get the actual estimate of the class size, we're going to need a control for income in this way. And similarly, you could add in gender here. You would have to first do this encode first, and I think I've asked you to do that. So you do encode gender, generate some sort of factor, and then you could add gender in there, and then you could control for both income and gender. It might be the case that girls do better on math test scores, and there's more of them in the small class sizes or something like that. But that's the overview of that. We'll wrap this up in class. Hopefully that is useful. Take a look through this do file and make sure you're on the same page as this.